Hi students, this is a continuation of chapter 22 on electromagnetic induction. Okay, so this is part 2. Okay, so so we talked last time about, in the first video, we talked about Faraday's law of induction. And again, there's a lot of conceptual details to that. It's I would say it's a relatively abstract law. I think all the Maxwell equations are probably, you can kind of consider as relatively abstract in their most general form. Faraday's law of induction, deals with something that, that we're really talking about an interaction, between, that I don't think we would actually expect, initially, the concept of a current being induced by a change in magnetic flux. I don't think one would initially expect that. I think that's probably maybe one of the more surprising laws, if you will, the way it works out for the student who sees it for the first time. So anyway, what we're going to do now is, as we normally do when we have a new law of physics, we try to utilize it in some way. And so we're going to utilize this concept of electromagnetic induction in a few ways. We're going to see how vitally important this law is to our way of living. So the first thing we're going to look at is called electric generators. All right, so electric generators, we're going to see that they're very similar looking to motors. So remember what a motor does. A motor converts electromagnetic energy, electric energy, magnetic energy, how I like to put it, to mechanical energy. I'm trying to be very generalized here. Okay, so it uses the concept. It uses these pole-faced magnets to turn a shaft, and that shaft does what? It runs some sort of a motor. It runs our motor in your car, motor in your lawnmower, whatever motor you happen to have. I mean, it's a motor that any motor operates by converting electromagnetic energy to mechanical energy. Now you have the concept of an electric generator. Electric generator, what it does is it converts mechanical energy to electromagnetic energy. Goes the other way around. So, when you have a large, powerful storm that comes through and knocks out your power, sometimes what you have to do is you have to go out and get your generator, put gasoline in your generator, and then your generator does what? It operates the generator then will take the gasoline, the chemical energy from gasoline to operate what we're going to discuss as electric generators, and it's going to give you electrical energy. So your lights will be able to go back on. You'll be able to actually run your electricity in your, at least some part of your house based on the generator. And of course, you can think of your power plant in and of itself that gives you electricity in the first place as nothing but a big generator. All right, and so we're going to look at, we're going to draw a little picture here of what a generator looks like, and it's going to look really similar to a motor. So with the generator, we're going to have these pole faces. So I have the north pole face over here. Again, this is not a north magnet. It is the north end of a magnet. So in reality, there is more magnet back here. This is just the north face of a magnet. Remember, magnets can never, their poles can never be separated. Now we have something that looks similar. We have a shaft. And we'll have we'll do a rectangular loop like we did in the past. Make it symmetrical. Okay, and then we'll have a south face magnet. Draw a little further away. Well, all right. And of course, this is the south face of really a magnet, right? I mean, there's a north pole behind there someplace, right? You're not just going to get south face magnet. You're not just going to get a south pole by itself. Now, what's going to happen is we're going to expect there to be some sort of an angular velocity of this. This is going to be twisted at some angular velocity. We're going to go back to, we're going to actually talk a lot about rotational kinematics again, like that we had back in chapter, back in physics 1. Now, of course, there are magnetic fields going across, as we normally would expect. The magnetic fields coming straight across, that's the magnetic field lines, I should say. And then we can think of there being an area normal to this face of this generator. And we can think of the area normal as forming an angle theta with respect to the magnetic field. All right, so theta is the angle of area normal. So basically the area normal of the wire loop face with the magnetic fields. All right, so again, the area normal, there's an angle with respect to the magnetic field. Okay, and then I think that's all the variables we need. And of course, we know that this the height of this loop, we'll say the height is L, and the width of the loop is going to be W. Same variables that we used with the motor, and there is an axis of rotation. And with the axis of rotation, there will be a width W/2 with one edge of the motor. All right, so again, drawing all this stuff out. Now, what's going to happen here is that you're going to use mechanical work. You're driving the shaft this time. Last time you used electrical magnetic work to actually drive the shaft. Now you're going to use mechanical work to drive the shaft and create electricity. All right, so last time you used electricity to give you mechanical energy. Now you're going to use, now the driver is going to be maybe a gasoline engine that's going to actually drive the shaft and give you electrical energy. So it's the exact opposite. All right. And so we're going to invoke Faraday's law. When we did the motor, we didn't have Faraday's law, but now we're going to invoke Faraday's law. Okay, so Faraday's law tells us that the electromotive force is going to be cap N if I have N turns of wire times delta P with respect to T. Again, delta P is the magnetic flux. So again, N equals number of turns of wire in the loop. All right. So again, that's just how many times you wind wire around to make this loop. Each one of those is going to have its own current going through. All right. So again, what I see here is that the magnetic flux is going to be the amount of magnetic field going through this this area. So the area normal is going to be very important. So the magnetic flux in this particular case will simply be B dot A, or B A cosine of theta. It's going to be something like that. That's going to be your magnetic flux. It's going to change, and of course theta is going to constantly be changing as this thing moves around. The angle between the magnetic field and the area normal is going to change. All right. So again, this is going to be theta is going to depend on it's going to be time dependent. All right. Now we're going to use here though is the concept of the motional EMF. All right. So if we look at, again, let's kind of talk about the top and bottom portions of the wire, and again, we've derived emotional EMF at the end of the last video. But if we look at the top and bottom portions of the wire, so if we look at this, so the wire is made of a conductor. So it has many free charges. When I say many, we're talking about 10 to the 8th per meter cubed, many, really large number of available free charges. Every free charge will experience the Lenz force law. It will experience a magnetic force equal to Q V cross B. Right? Every single one of them is going to experience that kind of a force. All right. So in that particular sense, there's going to be a current, that's going to happen. So just because these charges happen to be moving, so let's take a look at the top. Well, let's take a look at the let's say the left side for a moment. So imagine in the left side, I have some charge sitting in this conductor. Now, where is it going to move? If the motor is going to go, if it's going to be forced to go in this, I guess this would be, if I'm looking straight down, this would be a counterclockwise motion. My eye is coming straight down looking at it. This charge is being forced to move outward, right? In this current situation, it's being forced to move outward. So its velocity, its particular velocity is going to be what? It's going to be looking at it's going to be a QV coming straight at you right now. Again, I'm talking about the left side of the wire. I'm just talking about one charge, left side of the wire, QV. And where's B? Cross B is going to be pointing up. All right, and so we're talking about that there's going to be current. Then the charge is actually going up. The current would then be going down. So you're going to have current that's going to be going basically being pushed down in this particular situation. All right. So if you look at this, each charge is going to actually be given some sort of a current, some sort of a force that pushes these charges in this arrangement. All right, and it's really just thinking about the charge itself moving. Again, it's an individual charge moving a magnetic field. So as it moves around, spins around in a circle, it's always going to be feeling what? It's always going to be going, it's always going to be feeling a force that's going to be given by some sort of velocity. And it's going to be, it's really going to be the, it's not going to be the, it's going to be the component perpendicular to the magnetic field. All right, so it's going to be, so it's really not going to feel the full velocity all the time. It's only going to feel B sine theta, right? Because again, if I look at QV cross B, you know, what is that? Well, it's going to be QV B sine theta. So it's going to be QV B sine theta. And so so I can actually move the sine of theta back. And so I can basically commute these. So what I really have is I can put the sine of theta after the B. And so really the only component of the velocity of a particular electron that matters is the component perpendicular to the magnetic field. And that is going to change. Why? Because theta is constantly changing. All right. And so in this particular case, you're always going to have, at some sort of a sinusoidal manner, you're always going to have the velocity having some component either perpendicular or parallel to the magnetic field. So when it's coming straight at you like it is right now, that's going to be sine of theta is what? 90. So that's going to be a maximum, sine of 90. However, when it comes all the way around and points along with the magnetic field periodically, now they're aligned. Now it's zero. It's going to go through zero. And then it's going to go through a maximum. Then it's going to go through zero, and so on and so forth. So it's going to be, so again, the portion of the velocity of this individual electron that really matters is going to be its component perpendicular to the magnetic field. All right. Now, so essentially, what I'm going to say here is that in the vertical portions, the vertical segments of this wire, in the vertical segments, so if we consider one particular electron, it's any one of them out of the many, many possible, let's just pick one particular electron, in one of the vertical segments, it will experience a vertical force given by F equals Q B sine theta. Again, I kind of mixed things around here. I showed you how I was able to put sine theta together. So really, the vertical force depends on the perpendicular on the component of the velocity of the electron velocity, a little e minus to save space here, perpendicular to B. And that will vary. Okay, that's going to vary. Okay, that's going to vary in time. Okay, so now that's true for the side segments. Again, I talked about the vertical segments. What about the top and the bottom segments? Well, the top and bottom segments, what are they going to experience? Well, let's just say the way it is right now. Let's imagine here for a moment. Let's imagine that this has been turned a quarter turn, so that the top segment, let's say, is a line coming at you. Well, in that particular case, let's just say, for instance, that okay, if my electrons are being pushed down, let's say I have now electrons coming at you. All right, so what's that going to be? QV coming at you cross B. Again, I'm imagining that I've turned this a quarter of a turn, right? So this has now been turned a quarter of a turn, right? So now it's coming straight out at you. So it'd be QV cross B in this case. So it'll be straight up. And so essentially what I'm going to end up having is either straight up or on the other side, QV cross B. Oops, I'm sorry. Let's see. This way. So it'll be this way. So QV. I'm sorry. Let's see if I'm going this way. Then this bottom portion is going to be going into the board, but the top portion is coming out of the board at you. At the same time, the bottom portion is going into the board. So again, QV cross B will be pushing down, right? So at any given time, I'm going to have the top and bottom segments. You're either going to have forces pushing the currents, pushing the electrons toward the top of the wire or the bottom wire. They're not going to actually contribute to the current. The only portions of the wire you're going to have electrons contributing to a force, either pushing the wires one way or the other along a direction with respect to the current, with respect to the actual wire loop segments, is going to be on the side wires. The top wires, the top and bottom portions of the wire is not going to contribute to the current. All right. So again, looking at this logic, again, just like with the motor, I'm not going to have to really worry about the top and bottom portions of the wire. So the top and bottom portions, so an electron in the top segment of the wire will experience a force. F is QVB sine theta. That pushes it to the top of the wire. All right. Likewise, an electron in the bottom segment will be pushed to the bottom of the wire. Again, by the magnetic force. All right, so magnetic force is either going to push electrons either to the top of the wire in the top segment or to the bottom of the wire in the bottom segment. They're not, so the electrons in the top and bottom portions of this wire loop they're not going to participate in the current. They're not going to contribute to the pushing of the wires of the electrons to make a current. All right, so what that basically means is that the electrons in the top and bottom portions of the wire will not contribute to the current. So the electrons in the top and bottom wire segments will not contribute to the current in the wire loop. We only have to really worry about the side wires, the side segments, the vertical segments, all right? So again, from the same argument, like I said with the motor, I don't have to really worry about what's going on in the top and bottom portions of this wire. Only the side portions of the wire matter. All right. So, and I discussed the side portions of the wire. Now, what did I say last time? Remember, I gave you the example of the airplane or the wingspan in the last lecture. You know, if I imagine that there is some sort of a vertical wire that's going through a magnetic field, I can think of a what's called a motional EMF. All right, and so the top and bottom wires, again, this is just like, you know, the example of the last problem I worked out. What was that problem? Let's go back to it here. I worked out problem, yeah. So recall in Openstack's 23.17, okay, the section of the airplane, or we'll say the wings, so the two wings taken together, the wing section of the airplane wingtip to wingtip acted as a conducting wire moving through a magnetic field. B. So you look at it, you know, I think the magnetic field is everywhere into the board. So I'm just going to draw a simplified diagram here. So I have this object. It has a length L. It is moving at a velocity V. And it's going through some sort of a magnetic field. I'm going to kind of draw like the tail feathers here of this magnetic field that's going basically into the board. Kind of imagine it's going into the board. So this is my velocity V particularly. And I said that, yes, there is what we call a motional EMF. So I basically have this EMF epsilon given by B, L, V. And I call that a motional EMF. Okay, so essentially from Faraday's law, and we derived this actually, you know, when we talked about pulling the wire loop out of the magnetic field, we derived the motional EMF directly right from there. We have a portion. The portion that really matters is this vertical portion of that wire loop that's being pulled out at a constant velocity V. We derive this concept of a motional EMF. Basically, you have a segment of conductor going at a velocity V in a magnetic field B. And the EMF, which we derive from Faraday's law of induction, is BLV. All right, so that's what the EMF actually is. So the EMF for either of these vertical segments of wire in the generator is a motional EMF. It's epsilon's BLV. All right, and so we can go, and again, we've derived this already a couple of times. So let's write this down. So this, for the side wire segment, just like we did, you know, just like we did with the wire, we're pulling out the rectangular wire loop from the magnetic field, just like we did with Openstack's 23.17. We derive a motional EMF. So each vertical segment of wire experiences a motional EMF. Motional EMF. That's where we get started with this. We care only about the vertical segments of the wire. All right, and that's going to be epsilon is B L V. Again, that's each wire, right wire and the left wire, is each going to experience an epsilon equal to BLV. Now, of course, as I said, the only component of the velocity that matters at any given time is the vertical component, right? So again, only the vertical component of velocity, only the component of the velocity vertical only the vertical component, only the vertical component of the velocity with respect to the magnetic field matters. And that's because of Lorentz force law. So I would write a sine of theta right here. Instead of V, it's V sine theta. Now, what's the difference between this and the airplane flying, or me pulling a wire straight out of the magnetic field? Why? Well, because I'm constantly pulling the wire out of the magnetic field in the same manner. There's always a velocity lined up with the force every single time. Same with the vertical, same with the airplane. The airplane is always flying parallel. Here's the magnetic field. Every single time, according to my airplane's parallel magnetic field is always going to be perpendicular to it. Whereas in this case, I have a wire where sometimes the magnetic field is perpendicular and sometimes it's parallel. So again, in this particular case, I have this circular motion going. I have this vertical section of wire, and it's constantly seeing a different vertical component of the magnetic field. It gets a different view of it per unit time. So unlike the other two problems, I have to deal with this concept that is that there's constantly a change of this angle. Sometimes I get zero, sometimes I get max. There's an angular variation with respect to this velocity this time. That's how it differs from the previous examples that I've shown for motional EMF. So the difference is there's this angular dependent based upon the angle between the component of velocity of the electrons in the wire, which happens, by the way, to be lined up with the face of the wire. So normal face of the wire and the component of velocity of any given electron in the side segments always lines up. So that's the same angle that the normal face makes with the magnetic field. All right. So that's my motional EMF for this particular situation for the generator at BLV sine of theta. All right. Now that's just one segment of wire. I have right and left, right? So I have to multiply this by 2 to make up for the fact that I have 2 vertical segments of wire. All right, so there are 2 vertical segments of wire. Each of them is going to contribute in the same way, left and right. So that's going to be epsilon is 2, not 2 because of the 2 segments of wire, BLV sine of theta. Okay, so I'm developing my equation right now for the EMF in this particular arrangement. All right. Now, let's understand here that I'm trying to get a time-dependent relationship. And so far, you do not see time explicitly. Well, time is actually implicitly. It's a parametric variable. If we think about it here, the time dependence is located inside of theta. So theta, if I imagine I go back to, again, rotational kinematics. Again, we're going back to physics 1. Rotational kinematics. And it's going to be simple because there's going to be no acceleration, no angular acceleration. If I have an angular velocity omega, and I'm subtending an angle theta, basically the angle theta is the angle between the normal and the magnetic field. Well, that's going to be done at a constant rate. Theta equals omega t. That's my d equals vt for rotations. The displacement, angular displacement equals omega angular velocity times t. All right. Again, that's my simplest formula in rotational kinematics. That's the equivalent of d equals vt for translational kinematics. So I can stick that into this formula right here. So there's my time dependence. I now then have epsilon equals 2 b l v sine of omega t. Okay. Now I have explicit time dependence, utilizing the most basic rotational kinematic equation I could find. Now, I really want to get everything explicitly written as kinematic variables. So I have this velocity. This is a tangential velocity. Again, this velocity here is the velocity at any given time that an electron is going to feel. And again, it's always a velocity that's going to be, again, I've already worked out the details that's the normal component velocity. This v right here now is the actual magnitude of the velocity, right? And that's always going to be an orbital velocity with respect to this axis. So again, it's always rotating about the axis. I mean, essentially any given electron is almost like a planet, if you will. It's constantly going around this axis of radius w/2. All right, so let's write this equation up here. Is what we have so far. So what we have is any individual electron in a vertical wire segment is rotating about the central axis at orbital speed v and at a distance in the radius w/2. And that's my radius, right? So what do I know about that? Again, I go back to rotational kinematics again. I have something going around uniform circular motion at a radius w/2. What do I know about that? Well, I know a certain relationship that, again, we derived back in kinematics, in our study of kinematics, and that is, remember this relationship, B equals omega r. If I have something going around a circle and its radius r is going at some orbital velocity v, and again, this is at right angles, tangent, again, I get B equals omega r. Well, I know what r is, right? In this particular case, the central axis, any given electron in the side segment is always orbiting at a distance of w/2. So my v, my r is w divided by 2, half the width. And then I have omega. I can stick that in for v. And now I'll have nothing but angular variables, and the rest of it being geometry. So let's put this in for V. And then what do I have? Well, now I have epsilon is 2B L W over 2 omega, right there, sine omega t. And make sure your omegas and your W's don't look exactly the same. My my omegas oftentimes look like my W's, so I have to be very, very careful. All right. Megas are the Greek W, right? So we have now, so then we can actually do what? We can actually cancel out these 2's. Okay, that's nice. Then we can realize, hey, L times W, isn't that the area? Yeah, that's the area. So the area of my wire loop is LW. So let's fix this up. Now I have epsilon is going to be AB omega sine of omega t. All right. If so, let's put this up in the top. Now this is my latest equation. Epsilon is now the area times the magnetic field times the angular velocity times the sine of omega t. That's what I have so far. So let's put this up in the top. And I have one more fix up to do. All right. So latest and greatest epsilon is A B omega sine of omega t. Now it doesn't really matter if my omegas look like W's anymore because W is gone. All right. If there are n turns of wire in the wire loop, then each turn of wire is itself contributing epsilon is A B omega sine of omega t. Each one of those is. So I'm going to have a whole bunch of them added together. That's going to be n of them. So how do I fix the equation up? Well, it's real easy. I just multiply the front of it by n. And that is my final equation for the electric generator. EMF and electric generator. So this is my equation. Epsilon is NAB omega. Let me write this prettier. So epsilon is NAB omega sine of omega t. Okay, what is that? That's the EMF induced in a generator coil of n turns. This is the EMF induced in a generator coil of n turns. All right, so this is a direct application of Faraday's law of induction. The EMF induced, I mean, there is no battery located here. Okay, literally, we're causing a loop to rotate in space, to move in space with respect to magnetic field. The individual electrons that are in these vertical segments of wire are experiencing Lorentz force law individually. And altogether, because of Faraday's law of induction, because we derived the concept of the motional EMF, both of these side segments of wire are experiencing a motional EMF directly based on Faraday's law of induction, And as we see, there is an EMF induced in this wire loop. That's basically based upon the wire loop rotating about, and it's given this way. Now, does this, and again, I can also get the maximum or peak EMF. I mean, I can understand, well, I mean, again, N is constant, the area is constant, the magnetic field is constant. Omega is also constant. It's a constant angular velocity. What varies in time is the sine function. Well, kind of like what I said with the motor, if I want the max, I maximize out the sine function. Let the sine function go to a max value of 1. Sine of 90, or sine of pi radians would be 1. All right? Or sorry, sine of pi over 2 radians. I apologize, not pi. Pi is 0. Sine of pi over 2 radians is 1, or 90 degrees. But we want to do radians here because that's what the actual measure in a trigonometric function is always radians anyway. Degrees is kind of convenience for us, but the actual base angular measurements for any kind of a sinusoidal or any kind of trigonometric function is always radians. But the max would be that we know the maximum value of this sine function is 1. So it means the maximum EMF that this wire loop can experience is NAB omega. That's the maximum. This is the time varying EMF induced in the generator, and this is the maximum value you can expect in the generator. Okay, so does this make sense? Well, it makes sense that clearly, you know, if one loop, if one contribution of a wire contributes, you know, a certain amount, well, N wires are going to contribute more. So clearly, epsilon max should depend on N. More wires, the greater the induced EMF. That makes sense. The area, well, the area makes sense too. You know, again, the larger the area again, the larger the area, the greater the distance that the wire, that the individual electrons in the vertical wires are going to, they're going to experience a greater there's going to be a greater amount of contribution they're going to have. They're going to be further away from the actual axis. If we go back to your equation, you know, again, you know, that W over 2 comes directly into the orbital velocity. And so again, what would I have if I decided to take the same omega and expand out my W? I'm just going to have a larger orbital velocity. So that makes sense that the area would depend on that. And of course, the area also depends on L. So yeah, that also makes sense. The bigger the coil, simply the greater the induced EMF. The greater the magnetic field, the greater induced EMF. That totally makes sense too, because the magnetic field comes directly into this equation from the Lorentz force law. So again, you know, the greater the magnetic field, the greater the induced EMF. That, you know, again, it goes straight from BLV. You know, B, greater the B, of course, the greater the EMF. The greater the L, the greater the EMF, and the greater the V, which depends on W over 2, which depends on W, and hence depends on the area. All of that makes sense. What's a little bit more surprising is the dependence on omega. And I think with omega, you can kind of see this if you see, you know, if you look at, I always kind of see, it's the best way to looking at this. If let's say you have a cheap bicycle generator, you notice that as you go faster on your bicycle, your light gets brighter, right? And so the fact is, you know, the cheap variety of a bicycle generator, you'll definitely see this dependency on omega. So yeah, so it's definitely a dependency on omega as well. So all that makes sense. All right, let's work out some problems now. I'm gonna do Openstack 23.28. All right, Openstack 23.28. See what we have. All right, this guy is seen better days. All right. Remember to put the cap on my pen when I start talking. All right, here we go. Here we go. Openstack 23.28. 28. That one says calculate the peak voltage. Of a generator that rotates its 200 turn 0.100 meter diameter coil at 3,600 RPM. Numbers here. And in a 0.800 Tesla field. So a bunch of numbers. All right. Calculate the peak voltage. So peak means maximum, right? Calculate the peak voltage of a generator that rotates its 200 turn, that's N, cap N, 0.100 meter diameter, there's your R, or your D actually, your diameter, 2 times R, coil at 3,600 RPM, that's your omega. And a 0.800 Tesla field, that's your B. All right, so again, picking all these things out. So I'm gonna erase this for real estate. Okay, so how do we do this? So we go back to our original formula for the maximum. So again, as I said, I'll call it epsilon naught, the maximum value of the epsilon. I mean, I like to write typically epsilon as epsilon naught sine of omega t. That's what I typically like to write. So I'll typically write the maximum as epsilon naught, not the permittivity constant. All right, so epsilon naught is going to be NAB omega. All right, so I need all of that information to be able to do this. So N, they gave that to me as 200. Great, that's done. A, well, the A, I'm saying that there is a diameter of 0.100 meters. So I have to find the area. So the area is pi d squared over 4, or pi 0.100, again, area of a circle, meters, 20 squared over 4. A is going to be 7.85 times 10 to the negative 3 meters squared. All right, great. That's my area. How about magnetic field? Magnetic field, yeah, I was given that as well. That's going to be 0.800 Tesla. And omega, what's that? Well, I'm giving that an RPM. That doesn't help me quite yet. I have to convert, right? So they're giving me omega as 3,600 revolutions per minute. Again, this goes back to kinematics. I want radians per second, so I need to get rid of revolutions. So there's 2 pi radians in a revolution. One time around a circle is 2 pi. Get rid of revolutions, they cancel. Minutes, got to get rid of minutes. So minute goes on top, 60 seconds goes on the bottom. When I work all this out, I find that my omega is 377 radians per second. Great, there you go. All right, so that's all I need. And let's put it all together. Epsilon naught is 200. That's my N. My A is 7.85 times 10 to the negative 3 meters squared. My B is 0.800 Tesla. My omega is 377 radians per second. All right. Putting all that, multiplying all that together, I find out that my epsilon naught is going to be 473.5 volts. That is the maximum induced voltage or EMF I'll have in my generator. 473.5 volts. And it's straight from what I derived. Okay, let's do another one of these generator problems. 23.30 Openstacks. That says, what is the peak EMF generated by rotating a 1,000 turn uh, 20 centimeter diameter coil in the Earth's .00 times 10 to the negative 5 Tesla magnetic field. Given the plane of the coil is originally perpendicular to the Earth's field. So read this very carefully. And is rotated to be parallel to the field. Parallel to the field in 10.0 milliseconds. All right. So what is the peak EMF generated by rotating a 1,000 turn, 20 centimeter diameter coil in the Earth's 5.00 times 10 to the negative 5 Tesla magnetic field, given that the plane of the coil was originally perpendicular to the Earth's field and is rotated to be parallel to the field in 10.0 milliseconds. So again, we can pick all the information out of this. N equals cap N is 1,000 turns. The diameter is 20 centimeters. So it's a circle. The magnetic field B is 5.00 10 to the negative 5 Tesla. Now, we have to be really so we have to be really careful about how we're thinking about this now. So we're going to start off by saying that the plane of the coil was originally perpendicular to the Earth's magnetic field and is rotated to be parallel. So the plane of the coil, as if you took the coil would reside in a plane. So originally a coil, if I look at it edge on, here's the face, right? So the circle is kind of like into the board. So there's the plane of the coil is actually, I'm sorry, the magnetic field is straight down. The plane of the coil will be like this. Here's the magnetic field straight down. The coil is originally perpendicular. And in 10 milliseconds, it's going to go to parallel. So it's going to rotate from perpendicular. In 10 milliseconds, it's going to rotate to be parallel. So that's a quarter of a rotation. All the way around is is 360 degrees. Here we're going from parallel 0 to say -90. Okay, that's a quarter rotation. Keep that in mind. It's going to do a quarter rotation in 10 milliseconds. All right, you got to read that very carefully. All right, let me erase this and let's work the problem. All right, so first of all, as I just said, well, let's see, n equals 1,000. So let's write down what I know. I know that n is 1,000 terms. Okay, right off the bat, I know that. I got to find the area. So again, what am I looking for? I'm looking for eventually the maximum. I want the peak EMF. So again, that's going to be epsilon out as N, A, B, omega. All right, so I have to answer the mail on each one of these. So I found N. I mean, that's given to me straight out. The area, again, I'm given a diameter. So the area is going to be, again, pi times the diameter squared divided by 4. Or the area is pi times the diameter is, again, it's we're told the diameter is 20 centimeters. That's 0.20 meters squared divided by 4. The area is going to be 3.14 times 10 to the -2 meters squared. That's my area. That answers A. B, I'm being given B. I'm being told again it's the magnetic field of the Earth, 5.00 times 10 to the -5 Tesla as a magnetic field of the Earth at this particular location where it's happening. Omega. Well, what do I know? Well, I know that 1/4 of the period is 10 milliseconds, right? T is the period. So again, the period is how long does a cycle take? How long does it take for there to be an entire cycle? Well, we know that a quarter of a cycle is 10 milliseconds. How long is the cycle? Well, multiply both sides by 4. The whole cycle is 40 milliseconds, or 40 times 10 to the -3 seconds. That is one time around. Well, what do I want? I want omega. So I need to go back to my definitions of in kinematics, or even a wave theory, if you will, you wish. We always find out that omega is 2 pi divided by t. That's the relationship between angular velocity and the period. All right, and so you want to get that, so then you take 2 pi and you divide by what we just got done saying here, 40 times 10 to the -3 seconds. So again, I have to do a little bit of scratch work. So now I get that omega, when I work all this out, I get that omega is going to be 157.08 radians per second when I work this out. 157.08 radians per second. Okay, when I work this calculation. I now have everything I need. And so now it's a matter of just calculating the peak EMF. Right? So to do that, epsilon naught. 1,000, that's my N. My A is 3.14. That's 10 to the -2 meters squared. B, that's the magnetic field of the Earth. We're in the room here. 5.00 times 10 to the -5 Tesla. And if I have enough space, 157.08 radians per second. All right, really have enough there. Again, Na, B, omega, as you see written. Epsilon, again, this is epsilon naught. Epsilon naught, if I multiply all these 4 numbers together, you get 0.247 volts. Again, just to kind of clear up this little number I tried to write on the side there, that number is the angular velocity, 157.08 radians per second. So that's what's written in that corner over there. reaching. There you go. So that's what I try to write in the corner. So you're basically multiplying these four numbers. Omega is this number right here. All right. Electrical generators, done with that topic. All right, so now the next topic is we're talking about, we're I guess in the same concept of a motor and a generator. Let's kind of go back briefly to the concept of motors. And now, as I said, and when I did the derivation for the electrical generator, I said it's very similar to that of a motor, right? And so we go back to a motor, so again, electrical generators. And motors have a very similar construction. Recall, again, the a motor converts electromagnetic energy. Fly dive bombing me here. Fly. To mechanical energy. So it uses electromagnetic energy to drive the shaft, right? And on the other hand, an electric generator uses mechanical energy. It's going to, maybe a gasoline motor or a gasoline, engine. So electric generator uses mechanical energy and converts to electromagnetic energy. But they look very similar. All right, so they're very similar in construction. Now, let's go back to the motor. So again, this is that was a chapter 21 topic. So with the motor, the shaft is being turned. By electromagnetic energy. Or we'll say electromagnetic means, if you will. Again, we can remind ourselves what that was by going back to chapter 21's lecture. But let's think about this for a moment here now. If a motor is turning a loop, and what we just got done talking about a minute ago is that when you turn a loop, you generate an EMF. That means that Faraday's law is going to also come into context here. And let's think about this for a moment. If you are turning a loop, you are changing the electromagnetic. You're changing magnetic flux through the motor. And Lenz's law, going back to Lenz's law opposes change. Okay, so by whatever means, whether it be a motor or what have you, if you are changing, if somehow along the line by one way or another, that coil is being rotated such that the magnetic flux through the wire loop is changing. Lenz's law must come into play and oppose that change. Okay, so Lenz's law. So again, this rotation of the wire loop in the motor, and back to the motor now, in the motor, is a change of magnetic flux through the wire loop okay. Lenz's law seeks to oppose this. Again, Lenz's law always wants to oppose that change. So Lenz's law seeks to oppose this change. Lenz's law does not like change. Lenz's law wants to oppose change. Lenz's law seeks to oppose this change. So an opposing EMF is set up. And this EMF is called the back EMF. And so when you are rotating, something via a motor, there will be an opposing EMF because of the fact that you're changing magnetic flux through the loop. Now, when we first talked about motors, we didn't know about Faraday's law. We didn't study Faraday's law yet. By the time we got done with chapter 21, you only knew amperes. You knew Gauss' law and Ampere's law. This chapter 22, we talked about Faraday's law. Well, now we got to go back and show how Faraday's law now applies to the motor. And so, yeah, you are rotating. This is how you operate. You're a lot more likely to, in your day-to-day life, have contact directly with a motor than you are a generator. Because the power plants that run your house would be like a giant generator, and of course, if a big storm happens, you have to go break out. You have to go find electrical generators and break that out, put some gasoline in, and get that going. But the reality is, in your life, in most things you operate, it's going to be a motor. And so that motor is going to rotate a coil in a magnetic field. And that coil is the fact that coil is rotating in a magnetic field, the magnetic flux through that coil is going to change with time. That change in magnetic flux is going to cause, Lenz's law says, oh, I don't like that. That's a change. I'm going to oppose it. I'm going to set up an EMF just to oppose that EMF that you were generating. All right, and so essentially, every time you have a motor, you also have effectively a generator too. You have this EMF that's generated. All right, and so it's called the back EMF. All right, and so now you see this EMF, and again, I'm going to work a couple problems that I kind of understand. Because so essentially, this is, so essentially, I can kind of summarize it up like this. A motor, as a motor rotates the shaft, or sorry, rotates the wire loop, or it rotates its wire loop. Essentially, the rotating wire loop now acts as a generator. Creating or inducing a how would I put it? What's the word I used? I guess inducing a self-generated EMF due to Lenz's law to oppose the change brought about by the action of the motor. All right. So again, this is called a back EMF. Now, what's important here is to remind ourselves of the EMF relationship. Remember the EMF relationship. So recall a generator EMF, we just talked about this, is given by, again, epsilon is N A B omega sine of omega t. The important thing here is that the generator EMF depends on omega, the angular velocity omega. Which means the motor has to actually be working to generate the back EMF. So to generate the back EMF, which we oftentimes call epsilon sub B, the motor has to be rotating the coil. If you don't rotate the coil, you don't get a back EMF. And that's because of this omega factor in the EMF calculation. So what does that mean? Well, initially, let's say I have a refrigerator. I first turn it on, or washing machine, some heavy equipment. All right. So originally, when you start a motor, you first turn it on, particularly heavy equipment. You first start a motor, there is no rotation of the coil, or I'm sorry, not the coil, the loop, i.e. omega equals 0. And so there is no back EMF initially. All right. So what does that mean? This means that all the current, so all of the current I naught, the initial current drawn only supports the primary EMF of the motor. What's the epsilon of the motor? So if the wire loop, has resistance R, then this current draw will be I naught is epsilon over R. Okay, that is going to be a very large draw, usually. Again, it's only going to, there is no back EMF. So essentially, it's going to be the largest current you could possibly pull. Now we allow, after we first turn it on, we allow the loop to start rotating. It'll go to an operating speed. It'll go to its operating speed. All right. So as it's going to its operating speed, it's going to develop the back EMF. So once the motor achieves its full operating speed, the voltage of the motor becomes the EMF of the motor itself minus the back EMF. Then the current draw needed, we already know the resistance of this, that doesn't change. The resistance of the wire loop does not change. Then the current needed, the current draw needed is I didn't say I naught, but I this time. That's going to be epsilon minus epsilon sub back EMF divided by R. All right. Now, this is a much more normal sized current. Okay, this is the current that the fully operating motor is requiring. So this difference, the epsilon could be maybe 120 volts, epsilon B might be 100 volts. So again, it's drawing a much smaller current than when initially. You take away the back EMF, now you have epsilon over R, now you have a large current. The I naught's a large current. So initially, when you turn on a heavy motor, particularly like a washing machine or a refrigerator or something, when it first turns on, you often notice that some of the lights in the nearby lights will dim because that current draw is very large. Initially, that current draw is very large because the worst thing you want to possibly do is turn on something, have the motor stuck, and then just be drawing current when the motor's not moving. You do that, that's really bad, because you're drawing the largest possible current and that is usually a very large current. You might flip a circuit breaker doing that. You want to allow the motor to fully be operating so that you have a back EMF that's actually, so the motors are always designed to understand that there will be a back EMF. And it's designed, you know, its resistance, everything is designed for that expectation that Lenz's law is going to come into play and oppose. And so it's going to expect that back EMF. And that, in fact, in this particular case, the back EMF actually works in your favor. Okay, let's work some problems out to understand this. All right, so let's look at Openstack 23.39. And this topic is the topic of the back EMF. Openstack's 23.39. That says, suppose a motor connected to a 120 volt source draws 10.0 amperes. When it first starts, and that's your I naught. A. What is its resistance? B. What current does it draw? At its normal operating speed. When it develops a 100 volt back EMF. All right. Suppose a motor connected to a 120 volt source draws 10.0 amperes when it first starts. Okay, that's that I naught. I just turned the motor on. I have no back EMF yet. What is its resistance? Okay, I can figure out the resistance either with no back EMF or with back EMF, depending on the problem. So again, you want to find the resistance. That's a constant of your system. B, what current does it draw at its normal operating speed when it develops a 100 volt back EMF? All right, remember these numbers. So we have the I naught given to us when it first gets turned on. All right, so it first gets turned on, part A. So when it first is turned on, it draws a very large 10 amperes. Okay, so right, I first turn on this motor, 10 amperes right off the bat. Now again, it's plugged into the wall. Epsilon's 120 volts. All right, resistance, I don't know. But we know that in the case of the initially the voltage, so initially the voltage is just epsilon, right? It's the voltage of the system is just epsilon. So if I want to find the resistance, well, I'm going to go to Ohm's law, as I said. I know enough information to figure it out. So again, Ohm's law is always V equals IR. So V is I naught R. There's your Ohm's law. I'm going to solve for R, the resistance. So R is going to be V over I naught, or in this case, it's going to be epsilon over I naught. Okay, and so my resistance R is 120 volts divided by 10 amperes. The resistance is 12 ohms. 12 ohms, that's my resistance. That's true throughout the entire problem. Whether the motor is just starting off or the motor is running at full capacity. 12 ohms is a factor, is a constant of this problem. All right, look at part B. Now I know the resistance. I can use the resistance now to figure out part B. Now part B says, now we're looking at running the motor at full capacity, full operating speed. We're being told that epsilon sub B is 100 volts. We already know what epsilon is. That's pulling out of the walls, 100 volts. Now, notice how close the epsilon B is to epsilon. So you're going to see so the voltage now in the system is going to be epsilon minus epsilon sub B. That's now your operating voltage. All right. And so now when you look at looking at applying Ohm's law, now Ohm's law says, well, okay, well, again, it's always B equals IR. I want to find right now the current draw when the motor's operating at its full operating speed. Okay, so now what's V now? Well, it's going to be V is now epsilon minus epsilon sub B. So epsilon minus epsilon sub B, the full-blown back EMF, fully developed back EMF, is now going to be what's my voltage. Now I'm going to solve for I. Well, I now becomes epsilon minus epsilon sub B all divided by R. Or I is simply going to be 120 volts minus 100 volts divided by 12 ohms. And you notice the big difference is that when at full operating speed, I only need 1.67 amperes. Before I needed a whopping 10 amperes. So I'm going to draw 10 amperes, huge current when I first start this motor. But when it's at operating speed, it's only going to draw 1.67 amperes. I mean, again, that's a large current for us. But for this motor, it's much smaller than 10. You couldn't operate something at 10 amperes. I mean, again, now you're only drawing 1.67 amperes. So when you turn on a big device, a big appliance, initially you're going to possibly have a very large current draw, and that's why you might notice your lights dimming briefly, because you're really dominating the circuit with a very large current draw. All right, let's look at one more back EMF problem, Openstack's 23.42. All right. The motor in a toy car operates at 6.00 volts. And that would be its operating epsilon minus epsilon sub B. Developing, oops, I'm sorry, that's battery. I'm sorry, that's epsilon. Further. Developing a 4.50 volt back EMF at normal speed. Alrighty. If it draws 3.00 amperes, at normal speed, what current does it draw when starting? Again, very similar to the last problem. So, reading this here, the motor in a toy car operates on 6.00 volts, developing a 4.50 volt back EMF at normal speed. If it draws 3.00 amperes at normal speed, what current does it draw when starting? All right, so let's write down what I do know. All right, let's find out what do I know in this problem. That's my givens. All right, I know epsilon of the actual battery itself driving this motor, 6.00 volts. I know the back EMF that forms when fully operational, 4.50 volts. Again, I'm looking right at my laundry list here. I know the current, I use I, when fully operational. That's 3.00 amperes. Current, draw, when or at full speed. What I want to know is what is the current at startup? That's what I want to know. All right. So again, it's going to be a very similar problem. I need to find a resistance. So I don't know about the current at startup, so I don't have enough information really to discuss. I mean, I need the resistance to be able to actually branch from information that I know when the motor is going at full operational speed to the motor at startup. So what am I going to do? Well, I know this. I know that epsilon minus epsilon to B is IR. Again, this is a situation when the motor is fully running. I'm going to solve for R. And when I solve for R, then I'm going to go and then figure out what is I naught when I make the back EMF go to 0. Okay, that's my plan. Let's solve for R. R is epsilon minus epsilon to B divided by I. R is, again, what are my numbers? 6 volts, 6.00 volts minus 4.50 volts divided by 3 amperes, 3.00 amperes. My resistance, R, which is a constant in this motor, is 0.50 ohms. Great. I know that now. So R is 0.50 ohms. That's another piece of information I now know I've just calculated. Again, I got that from my understanding. I had a full understanding of what the motor's doing at full speed. What I don't understand yet is what current does it draw initially. So right at full speed, it draws a 3 ampere current, which is actually quite large for a little toy car. Well, let's find out what it draws initially. So initially now, what I want to do now is I want to make the back EMF go to 0. So back EMF now goes to 0. And now I'm being told here that, well, now I have epsilon is I not R. So as soon as I turn this on, as soon as I turn the motor on, the motor's not moving initially. As soon as I turn it on, there is no back EMF. So at startup, I have to draw a very large current to basically account for the entire 6 volts. All right. So what current is that? Solving this quickly, I naught is epsilon over R. All right. So I naught epsilon is 6 volts. R is, again, I keep everything in SI. I'll have a current in amperes, 0.50 ohms. I naught is a whopping 12 amperes. All right. That is the huge current that I need to draw when I first turn on this car. Before the motor is fully developed and it's full speed and a back EMF is fully developed. Initial current I need to draw is very large at that point. All right, that's the concept of back EMF. Now we go to the next topic. Okay, so this topic is called transformers. Now, the topic of transformers gives you really the answer to why Faraday's law is so vitally important to our lives. Okay, concept called transformers. That's the next topic. Okay, so transformers let me start off basic here. Transformers do what their name implies. They transform voltages from one value to another. All right, so that's what transformers do. All right, and so give me one moment. All right. Where was I? Yes. So they transform from one value to another. So essentially we have transformers in everything. So many cell phones, laptops, video games, power tools, and small appliances have built-in transformers. That convert the 120 volt, or in some countries, many countries, 240 volts in many countries. United States is 120. Actually, most of North America is I think all of North America is 120. 240 is usually Europe or New Zealand and things like that. 120 volts to the voltage needed to operate the device. All right. So again, that's what a transformer does. So the device may not necessarily be able to be used at the voltage from the wall. Maybe it's designed to be used at a different voltage. So the transformer will transform to the voltage that is required for the particular device. All right. We definitely depend on transformers for our power distribution system. So, giving examples, we know, as we talked about earlier chapters, power is transferred over power lines at very high voltages. So power is distributed over power lines at very high voltages. Because, as I did in a calculation earlier, we need to reduce energy loss. And you do so that I squared R energy loss. So I guess let's be more specific. Reduce the I squared R power loss. All right, so in order to have a smaller I, you have to have a larger voltage. And so again, you have to transform power, across the city to your house or businesses at very high voltage. Of course, this was a big debate between Tesla and Tesla with Westinghouse, George Westinghouse, Nikola Tesla with George Westinghouse were on one side of the fence. They wanted what we have today. And Thomas Edison thought that having high voltage power lines was crazy. He thought that was too dangerous, too hazardous, And so he thought that was a bad idea. The reason why we have the ability to transfer power at very high voltages is because of the transformer. So a transformer steps down the high voltage, this high voltage, to a safer 120 volts at your electrical outlets. So a transformer will take the voltage from the electrical power lines, the power lines you're getting, from the power plant, and steps it down to a safer level for you. 120 volts or 240 at in European countries. So, but again, it's so that's really the purposes of your transformer. Now we're going to find out that that Faraday's law requires a time-varying magnetic flux in the transformer. So the current, the input current needs to be time varying. Or AC. That is why one of the most primary reasons we absolutely have to have AC currents, AC circuitry, is, as I talked about this in a previous chapter or 2 chapters ago, is because of this very concept that we have to have a step-down transformer. We have to minimize power losses when we transfer. So again, economies basically say that it's a lot easier or a lot cheaper to have one large power plant distributing power to many households and businesses than to have many more distributed or scattered smaller power plants. It's much better to have one large power plant, for one. And for you to be able to minimize power losses in the power lines, you need to actually have the power plant, the power transferred via very high voltage, In order to be able to make this even doable, you have to have a transformer that steps that voltage down. Transformers, we're going to find out very quickly, depends on Faraday's law of induction. So for the transformer to work, the magnetic flux in the transformer has to constantly be varying. How do you constantly have that be varying? Well, you're going to have a varying, time varying current. Time varying current means what? AC. Okay, so that's where it is so important that we use AC power in order to be able to have that's why AC power prevailed over DC. Okay, let's talk about the operation or the setup of the transformer. How does the transformer work? So I'm going to draw a transformer that's very similar to the one that Michael Faraday initially. So again, we can thank Michael Faraday for the design of the transformer as well. So I'm going to draw one that's very similar to something that he would actually utilize. One fact, you know what? Let me do better than that. Let me actually show you the picture in Openstack. I think that the picture in Openstack is and I'll redraw what's in Openstack. But let's kind of look at the picture first. So let me open up Openstack real quick. This is going to take a minute. Should have opened up earlier. Okay. All right. Let's see. Oops, I passed. All right, and I'm almost there. There we go. Share with you now. Okay, you should see a picture of what our basic transformer. Now, what this transformer is, this is really a magnetic core. Okay, and so what's going to happen is that you see on the left-hand side, you see P for primary, and the right-hand side, S for secondary. Again, I'll write this up on the whiteboard. The primary is essentially where you're getting your power. So that could be like, for instance, you're hooking up. You have a, let's just say you have a transformer, in your computer or something. So primary could be what's coming out of the wall. Your primary could be 120 volts coming out of the wall. Okay, what the purpose of the transformer is that you'll notice that there is a coil around this magnetic core. That coil is going to have a current going through that magnetic core. So that coil is going to, you're going to have a current that's going to go around, wrap around that coil, and by Ampere's law, there will be a magnetic field going up that core, up the magnetic core. The magnetic, because of the way the magnetic core is established, the magnetic field lines will be trapped around that core. It'll actually go around the core. So the way these are drawn, they're going down and around, and it's going to go up the other side. Well, now you have the opposite situation happening. Now you have a magnetic field that's going through the secondary coil, and because you have a magnetic field going through the secondary coil, you're going to cause a current to be generated in the secondary coil. Now we're going to find out that the number of coils you want to have a step up or step down transformer, it's going to directly depend on the number of coils, N sub P in the primary or N sub S in the secondary. And that's what so I'm going to draw a little picture. That's pretty much what I'm trying to draw. All right, so let me make more sense out of this here now. So I'm going to try to draw the picture that you just saw. Let's understand how this works. So here is the magnetic core. All right. Okay, and then let's see here. And this core is going to have an inside to it. So again, it has a thickness. All right, so, and then we have a coil going around the primary. So let's see, the current is going to do what? I think it's going down. Coil comes in and goes around the back. Around, goes around the back. And that is a current that's basically coming around like this. So it's going around the back. It's coming in. So this current is coming in, coming around the back. And so you're seeing the current wrapping around. And what's it doing? As it wraps around, the right-hand rule on the side is wrapping around like this. The current is wrapping around by the right-hand rule. My thumb points straight down. So I'm basically having magnetic field lines that are going through this coil. And this is a magnetic core. And this is a core. This is a magnetized core. So this it's going to trap these field lines to come around. They're trapped in the core, and they come back around. On the other side is another so that magnetic field on the other side is going to come around. Magnetic field is going to come around, and it's going to drive current to go basically, I guess, counterclockwise around the core on the other side. So again, I'll see current coming around. On the other side, so I must have a thing out here as well. Okay, so current is going to be coming around. Magnetic field is going up, so the current is going to be going around this way. Yes, this is my I primary, I sub P. So each of these currents will be I sub P, and the current over here will be I secondary, I sub S. All right. So, and then of course the magnetic field lines are coming around, going straight through, like so. And they come back around. All right, so let me try to draw these right. So you see what I'm trying to draw. These are these magnetic field lines. they come up. Okay, so this is a ferromagnetic core. Okay, that's what's happening here. So now what we have here is, this is a transformer. So you have, so across each of these, this is an input current, I sub P. There's going to be an input voltage across, where, let's say it's being plugged into the wall, and it's transforming to another voltage. It could be a higher or a lower voltage. And that we call that the secondary. So there are two coils that are involved here, a primary coil and a secondary coil. All right. So current I sub P enters the transformer at the primary coil. V sub P is the voltage across the primary coil. Okay, now I sub P, this is right here, the magnetic field. So by Ampere's law, by Ampere's law, a magnetic field is set up perpendicular in the ferromagnetic core perpendicular to the primary coil, or basically, I'll say perpendicular to the current I sub P, or along the axis of the primary coil. That's Ampere's law. Ampere's law says we have a current that's set up. The current is going around the primary coil. Again, we're looking at the primary, the left-hand side. The current is going around the primary coil, causing a magnetic field, a very strong, almost like a little solenoid, a strong magnetic field going straight down. Okay, so that right now we're at the left-hand side of this. We have a magnetic field that's basically coming straight down. This is caused by Ampere's law. So we plug the transformer on one side. We're getting a, say the outlet from the wall, from the house, from your house, has an input current, primary current, and a primary voltage. That's causing that current is going around this core in a counterclockwise manner. Clockwise manner. I'm sorry, clockwise manner, and is causing the magnetic field to go straight down at the primary. Okay, and that's what this writing is about here. Now, let's follow the field lines. I'm going to have to do some erasing. So we have the left-hand side. All right, the magnetic field lines are confined in the magnetic core, in the ferromagnetic core, and follow around the core. You get an additional benefit. The ferromagnetic core itself, the ferromagnetic core gives enhanced magnetization. So it gives an additional benefit because it is a ferromagnetic core. Now the magnetic field lines find themselves up at the secondary coil. All right, so now the magnetic field lines pass through the axis, or pass through the secondary coil, generating current I sub S by Faraday's law. All right, so again, the magnetic field lines are going around the core. They're confined in the core. They're getting further magnetization because of the ferromagnetic core itself. They come around the corner. Now they pass through the secondary coil. Faraday's law says what? Faraday's law says now, because the magnetic field is straight up in the secondary coil, my right hand curls around so that my thumb is up. That's going to create a current I sub S. Again, this is all Faraday's law. All Faraday's law. Okay. Now, what operates this? So again, I haven't talked about the voltages yet. Okay, and again, you know, I'm not talking about them yet. All I'm talking about is that there's a current. I haven't talked about the AC nature of this yet, right? There's a current coming from the primary coil. It's coming around like this, clockwise, such that I have a magnetic field going straight down, straight down. Those magnetic field lines are trapped. They come back to go through the secondary coil. Since the magnetic field now is up in the secondary coil, now those current, that I sub S, is now going to be what? It's now going to be counterclockwise. So I've described how the relationship between the magnetic field in the core and the currents via, Ampere's law. It's not Faraday's law. Ampere's law. Erase your notes. I have not talked about Faraday's law yet. Okay, so again, let me back this up. I hope I didn't screw my notes up earlier. Again, current is coming in from the primary, at the primary, wherever, maybe your wall. Current comes in from the primary. That current makes, goes around the coil, and it goes in a clockwise manner. Magnetic field, because of that, Faraday's law says by the right-hand rule, the magnetic field is going to go straight down. The magnetic field is going down the magnetic core. Because the magnetic core, it traps the magnetic field lines to go around, and further causes enhanced magnetization. Then it comes up through the right-hand side of the core. Now what? Now the magnetic field is straight up, and Ampere's law says what? We're going to have a current that's going to go in a counterclockwise direction in the coils there, in the secondary coils. And all I've talked about so far is nothing but Ampere's law, the relationship between current and magnetic field. Ampere's law, chapter 21. Okay, now we're going to talk about Faraday's law. Now, how do you get these voltages? Well, Faraday's law, now let's make one more statement here. Let's assume that the cross-sectional area of the magnetic core, of the ferromagnetic core, is everywhere the same. All right, that means that that's the area which the magnetic field goes through. That cross-sectional area is everywhere the same. All right, so the magnetic flux vis-a-vis in everywhere in the ferromagnetic core. Well, what is magnetic flux? Well, again, everything is lined up, right? The magnetic field and the area normal are lined up, so it's just going to be simply BA. A is a cross-sectional area, right? So magnetic flux vis-a-vis equals BA is everywhere the same throughout the ferromagnetic core. All right. All right. So that means that I'll have a magnetic flux. Well, if I have a magnetic flux and it's constant, I can't use Faraday's law. Faraday's law simply will not care. Why? Because Faraday's law requires a time varying magnetic flux. All right. So Faraday's law requires that this magnetic flux be time varying if it's going to be used. Right. So Faraday's law now we finally talk about Faraday's law. Faraday's law requires a time varying magnetic flux. All right. And so at the secondary coil, I mean, so we need a time varying current, now, i.e. an AC current, to give a time varying magnetic flux through Ampere's law. Again, that's just Ampere's law. Ampere's law just says, well, whatever current you pass through the loop, I'm going to generate a magnetic field. Oh, you want to vary your current in time? Fine. Your magnetic field, or i.e. your magnetic flux, will also vary in time. So again, whatever current that gets put in the loop in the coil, you're going to get a corresponding magnetic field by Ampere's law. Ampere's law doesn't care what current you feed it, as long as it goes through the coil, it's going to generate a magnetic flux. So what would Faraday's law be? Let's consider the secondary coil. Let's imagine that I have a time varying flux. Well, then if the magnetic flux is time varying here at the secondary, then Faraday's law at the secondary. So if, so essentially if I have, let me back up. So given that we have a time varying current, so given a time varying magnetic flux, at the secondary coil, Faraday's law states that that voltage across that coil, V sub S, is equal to negative cap N sub S delta phi sub B with respect to time. All right. Now, notice I said voltage, not EMF. Why is that? So typically, the resistance in a transformer is very small. So we can use voltages as well as EMFs. In this particular case, I can, instead of having epsilon, I can actually write V sub S because, and it turns out transformers are very, very efficient. The way they're written, you can assume very small resistance. In that particular case, then I can just as well write V sub S. So that is the application of Faraday's law. If you are giving me a time varying magnetic flux at this location here at the secondary, N sub S is the number of turns in the secondary. It's very important. So again, let's take a look at this. N sub S is the number of turns in the secondary. All right, so again, very important. So that's what Faraday's law tells us right there, that you're going to have this time varying magnetic flux. And, given you have this time varying magnetic flux, Faraday's law says, okay, well, that EMF, or I can use voltages directly at the secondary, is going to be negative number of turns of wire at the secondary times that time rate of change of the magnetic flux. Now, given that that the magnetic flux is everywhere the same, then the magnetic flux anywhere else along here is going to still be the same delta p sub B or delta p sub B with respect to T, including at the primary. All right. So at the primary, so again, let's just write this equation up here. We know this from the secondary. All right. So again, this is Faraday's law at the secondary. Secondary voltage is going to be negative N sub S delta phi sub B with respect to T. Great. Now, since the magnetic flux throughout the entire ferromagnetic core is the same, then the primary coil also experiences the same delta phi sub b with respect to t, the same time rate of change of the magnetic flux. And it's everywhere the same throughout the entire magnetic core, the entire ferromagnetic core. So you would also expect that this coil also receives the same time rate of change of magnetic flux. Now, let's remind ourselves, this entire process is being driven at the primary coil. So it turns out, well, what kind of relationship can I have at the primary coil? Well, it turns out that there is something, and we're going to talk later when we talk about inductance, that there is actually something called self-inductance. And so we actually can write the following. At the primary coil, the current is driving a change the time varying magnetic flux. When this occurs, Lenz's law creates an opposing EMF. And that's called a self-induced EMF, or basically opposing, we'll call it a self-induced EMF. Okay, so a little different reason. Turns out that that EMF will be given as V at the primary is negative N sub P, and that same delta phi sub B with respect to T. So again, the current is driving, the current at the primary is driving this whole process. And it turns out you'd see this in, I mean, we'll study this when we talk about inductors, that the current itself, when you're causing a time varying current in the coil, you'll get a self-induced EMF that'll actually oppose you. It'll actually oppose that change, and it'll actually end up being like a voltage drop in the circuit. And so what we get because of that is we get a voltage in a primary given by the number of turns in a primary times that same time rate of change of the magnetic flux. All right. So now, and again, as I said before, because the resistance is so small in a transformer, we can go straight to voltages. So now what we have is two equations. We have an equation that governs the voltage at the secondary coil, and we have an equation that governs the voltage at the primary coil. Notice that they do have something in common. They have the same delta phi sub b with respect to T. So why don't we go and solve both these equations for delta phi sub b with respect to T and eliminate it? Okay, so we have these two equations, one at the secondary and one at the primary. And again, remember, N sub P now is the number of turns of wire at the primary, or of the primary coil. All right, great. So notice though that delta phi sub b to t is the same in both. All right, and so delta phi sub b with respect to t is common in both equations and can be eliminated. If we do so, we get the following nice simple relationship, that V sub s over V sub p is equal to N sub s over N sub p. That is our transformer equation. This is one of our transformer equations. So a lot of more challenging math and concepts, but the final equation is quite simple. That tells us that to control whether we have a step up or step down transformer, if you have certain primary voltage, to control what the secondary voltage is literally nothing more than a ratio of the number of turns in the secondary coil over the number of turns in the primary coil. It's that simple. Literally, you can design the transformer by just controlling the ratio, the number of turns of wire in the secondary and the primary coil. Okay, that's your transformer equation. So step-up transformer is one where you have a primary voltage when you want to get a larger secondary voltage. A step-down transformer is when you have a certain primary voltage and you want a lower primary voltage, all right? So let me erase all of this. This is what we're after here. All right, so the step up and the step down transformer. So again, our transformer equation is simply going to be V sub s over V sub p is N sub s over N sub p. All right, a step up transformer is one where V sub s is greater than V sub p, right? You have a certain primary voltage, you want a larger primary voltage. Maybe you're operating an X-ray machine that takes maybe a kilovolt, and all you have is 120 volts coming out of your wall. So you'd want to have a step-up transformer for that. A step-down transformer is one where V sub s is less than V sub p. So maybe you have a video game or something that takes, a smaller voltage to operate, and you don't want to have 120 volts. You want to step it down. As an example, step-up transformer, step-down transformer. Okay, now we can actually create a couple more transformer equations. That's the main one. Now, let's talk about the concept of power. Now, assuming that the transformer has negligible resistance, then the electrical, so the input electrical power, so then the input electrical power equals the output electrical power. We can minimize power losses. And this is generally true in practice. Says most transformers have an efficiency that exceeds 99%. So most of them are extremely efficient, highly efficient. And so you can literally say that the input power, the power at the input, is equal to the power at the secondary. So what does that mean equation-wise? That means that I can say the following. So again, I'm talking about, electricity. And so, well, what's the relationship? Well, in general, power, we'll say power at the primary. Power at the primary is what? It's IV. Current at the primary times the voltage at the primary. Again, that's generally, if you're talking about a battery or anything else, I times V is the general equation for electrical power. And we're saying, well, that's also equal to the power at the secondary. That's also equal to I sub S, V sub S, which is the power at the secondary. We're saying that the power at the primary equals the power at the secondary. That means that you have this relationship at your hands as well. So I can also write that V sub S over V sub P is equal to I sub P over I sub S. And it's another transformer equation that I can now use. That's just straight from the concept that there's no power loss in a transformer. Write that up there. Another equation for me to use. So V sub S over V sub P is equal to I sub P over I sub S. That's another equation I can use on a transformer. And finally, I can combine these two. So we can combine these two equations and get one more equation. I sub S over I sub P. Again, that's I sub S over I sub P. That's the same as, and that's going to be N sub P over N sub S. All right. So again, I can have I sub P over I sub S. I can flip them around. I get I sub S over I sub P is N sub P over N sub S. All right. So again, directly substituting, I get I sub P over I sub S, and I'll just turn them both upside down. And I get I sub S over I sub P is N sub P over N sub S. That's all I did there. So again, those are my three equations that I can use. So I sub S over I sub P is N sub P over N sub S. And so I literally can determine, the current at the primary and the secondary based upon the number of turns, and the voltages of the primary and secondary based upon the number of turns. Those are the main working transformer equations. All right, so let's give an example of a step-up transformer. I'm going to look at Openstack's example 23.5. Okay, so let's keep these equations in mind. all that mathematics and physics I talked about earlier with the magnetic, ferromagnetic core and everything, and the Ampere's law, those are the nice simple results. So let's look at Openstack's example 23.5. In that one, I want to calculate characteristics of a step-up transformer. Okay, so I'm being told a portable X-ray unit. Let me write it down here, I guess. A portable X-ray unit has a step-up transformer. The 120 volt input of which, and that's right out of your wall, is transformed to 100 kilovolt output. Needed by the X-ray tube. So the X-ray tube requires a very high voltage. Okay. The primary has 50 loops. And draws a current of 10 amperes. All right. When in use. All right, so A, what is the number of loops in the secondary? B, find the current output of the secondary. Space on here of the secondary. Okay, so step-up transformer. A portable X-ray unit has a step-up transformer. So 120 volts, that's your V sub P coming out of the wall, the primary. Input of which is transformed to 100 kilovolts, that's your V sub S of the secondary. Output needed by the X-ray tube. The primary has 50 loops, that's your N sub P, and draws a current of 10 amperes, that's your I sub P when in use. A, what is the number of loops in the secondary, your N sub S? And then B, find the current output at the secondary, that's your I sub S. All right, so that's what it's looking for. All right, so erase the words and work out what we need. So again, you have a very high voltage is required for the operation of the X-ray tube. So part A, and what do we know? First of all, we know that B at the primary, and you have a big laundry list of stuff that you know. So B at the primary is 120 volts. B at the secondary is very large, 100 kilovolts, 100 times 10 to the third volts. N at the primary, that's 50 loops. N at the secondary, we don't know. I at the primary is, we're told, is 10 amperes. I at the secondary, again, this will be part B. We don't know that either. A couple things we don't know. All right, so we have to, so the real main thing here is to pick your best transformer equation you want to use. Well, the first question I'm being asked is, well, how many loops are there at the secondary? Well, first of all, what do I know? I know B sub S and B sub P, and I know N sub S. So I probably want to use the original transformer equation, because the only thing I don't know is N sub S. So I would write the original transformer equation down as, again, B sub S over B sub P is N sub S over N sub P. Again, that's one of my transformer equations that I know. Let's solve it for what I don't know. So we can solve this quickly as N sub S is simply N sub P times B sub S over B sub P. And then we can just literally put the numbers in. So N sub S then becomes N sub P, which is 50, and at the primary. V at the secondary is 100 kilovolts. And then V at the primary is 120 volts. I then find out that N sub S, when I do all this, I find out that N sub S, number at the secondary, is going to be 4.17 times 10 to the fourth loops. All right, so I can write that here now. I know this now. So now that's 4.17 times 10 to the fourth. I know that now. So I have 50 loops, the input, and the primary, that many loops. 4.17 10 to the fourth, right? So I know that much information. Now, given I know more information for part B, I can pretty much use I can use more equations now to solve for the primary current. So for part B, I want the primary current. So now I'll pick a transformer equation. I sub S over I sub P equals N sub P over N sub S. And I want to find I sub S in the secondary. I'm being given I sub P. I want to find I sub S. I can solve this for I sub S, was cross multiplying I sub P. So I have I sub S as just I sub P times N sub P over N sub S. And I can use this equation now because I now know what N sub S is from part A. Now it's a matter of plugging it in. So I want I at the secondary. That's I at the primary, big, 10 amperes. Now the primary number of loops, that was just 50. And the secondary number of loops, that was 4.17 times 10 to the fourth. I found out that my secondary current is very small. It comes out to be 1.20 times 10 to the negative 2 amperes. So when you have a large current, you have a small voltage. When you have a large, again, this deals with the power, right? Power is V times I. So if you have a small current, you have a large voltage. Small current with a large voltage. Large current, 10 amperes, with a smaller voltage. Again, I times V must always be true. Power is I times V. That's throughout the entire process. So that just means your I times V, you have to have the same power. So at the primary, oftentimes what you end up doing is you're switching for a small voltage and a large current and you switch it out for a step down, for a step up transformer, you switch it out for a large voltage and a small current. It's a very small current, but you have a very large voltage. That's a typical property of a step up transformer. Now, the thing is, you know, you ask yourself the question, well, as I have said, you want to have AC circuitry or AC currents for your the operation of your transformer. Now, could you do it with DC? Could you constantly have a switching on, switching off of a DC? Well, it turns out you can't do a switching fast enough. You still would have an anomalous looking a situation. And so give me a moment. All right, you're still going to have, so let me go and show you a nice little diagram. Let me go back to the book and show you why we certainly depend on AC currents to operate a transformer like this. So let's imagine, so the transformer requires time varying currents. So what happens if we decide, well, let's just try to fake it with some sort of a switch. All right, and so let's just say instead of having a nice time varying sinusoidal voltage, let's say instead we have this switching. So we'll have the primary switch on and then off and then on, then off. You know, we'll constantly have this square well situation going on. Well, by the time you get to the secondary coil, what you'd get is you have essentially a plot that looks like the bottom plot. So the top plot would be, maybe you can control the primary voltage by trying to fake a time varying well, you have a time varying situation where you'd have on and off switching very quickly. But you would find out that by the time you got to the secondary coil, your voltage will look like this. You can't, and then you know that is not a good voltage profile. That is not a good profile in order to be able to operate any kind of appliance. Appliances in today's world operate on sinusoidal voltages, and so you can't really avoid using AC currents. If you're going to operate any kind of appliance, you have to have AC currents. You have to have an AC voltage. So you have to have sinusoidally varying voltage. You can't get away from it. All right, so you cannot use DC. Okay, that's the long and short of it. All right, so now, so the idea is to operate a transformer, successfully operate a transformer. Transformers require AC circuits. There's no ifs, ands, or buts about it. You must use AC circuitry. All right. That is one of the primary drivers of why we have AC. Why we have AC. We have to transform. We have to transmit, I guess I would say, the power over the power lines of high voltage. There's no doubt about that. You have to distribute the power that way, by high voltage, in order to be able to reduce the power losses. I mean, I did a calculation a couple of lectures ago, and of course, in order to be able to use electricity safely, we'd have to have a step-down transformer from the very high voltage power lines to us, you know, in homes and businesses. So that requires a transformer. Transformers can only work with time varying current. Okay, we just saw that. I derived that. I proved that. You must have time varying current because Faraday's law requires a time varying magnetic flux. So when I said that Faraday's law was one of the most important laws, if not the most important law to our technology, that's why. Faraday's law will say that it will induce a current or induce a voltage, it will induce a voltage based or an EMF based upon a time varying magnetic flux. That very equation is what powers everything around you. All right, so that very equation powers everything. All right, so that is what gives us our technology. Faraday's law of induction gives us a technology that we enjoy today as in the human race. Okay, I'm going to look at Openstack 23.6, example 23.6. And that's for a step down transformer. The characteristics of the step down transformer. Okay, so what does this say? Well, I have again, it's like another large example. So I have a battery charger. Battery charger meant for a series connection of 10 nickel cadmium batteries total EMF of 12.5 volts DC. Needs to have a 15.0 volt output. To charge the batteries. Okay, it uses a step down transformer. With a 200 loop primary. And a 120 volt input. Okay, so a realistic situation. How many loops should there be in the secondary coil? space here. Okay. And B, if the charging current is 16 amperes, what's the input current? If the charging current is 16 amperes, what is the input current? All right. Okay, so a battery charger meant for a series connection of 10 nickel cadmium batteries, total EMF at 12.5 volts DC, needs to have a 15.0 volt output to charge the batteries. Use a step-down transformer with a 200 loop primary and a 120 volt input, pretty much all to the wall. How many loops should there be in the secondary coil? Okay, that's N sub S. If the charging current is 16 amperes, what's the input current? Okay, so the charging current's I sub S. We want the input current I sub P. That's all that reads. Let me erase all these words and let's write these in terms of values. All right. So my laundry list here. So here's A. So what do I know? Well, I know the secondary. So the secondary right at the charger, the amount of out voltage it needs is 15 volts. The voltage coming out of the wall, the primary, is 120 volts. So it's right out of your wall. Okay. And the number of coils in a primary, as we were told, is going to be 200 loops, we were told. That's the number of coils at the primary. We want to know the number of loops at the secondary. All right. And also, we know one more thing, that the current at the secondary is 10 amperes. Altogether, what we don't know is number of loops at the secondary and the current at the primary. These are the things we don't know. All right, so the first part is we want to know the number of loops at the secondary. So we go to the appropriate, the first transformer equation we derived, and then simply V sub S over V sub P is N sub S over N sub P. Okay, and so we solve for N sub S. N sub S is N sub P times V sub S over V sub P. And so number of coils at the secondary will be the number of coils at the primary, which is 200. And then V sub S over V sub P. So 15 volts over 200 over 120 volts. We find out that the number of loops at the primary, at the secondary, at the actual charger itself, is going to be 25 loops. All right, so we know the number of loops at the primary. That's right at the wall. We know the current coming out of the voltage coming out of the wall is 120 volts. We need to have a certain voltage at the charger. That's V sub S. And we don't know how many loops there are at the charger at the actual device. So we calculate that through a transformer. So the device needs to have 25 loops at the charger end of the transformer. All right, so we now know this, 25 loops. All right, and then we want to know what's the current at the primary. We want I sub P. To read the problem carefully. So we now want I sub P, the current at the primary. So again, we go to the appropriate transformer equation, and that would be simply I sub S over I sub P. is N sub P over N sub S. And so we go to the appropriate transformer equation, and we solve now for I sub P. So essentially flip over and multiply. We simply get that I sub P simply becomes I sub S multiplied by N sub S over N sub P. So at this particular situation, we're able to get this on. We're pretty much directly. So I sub S is going to be the 10 amperes. That's 10 amperes that's required at the charger. N sub S, we figured that out a moment ago. That's 25 loops. And N sub P, well, we know that was a given at 200 loops. So we find out that I sub P, the current at the primary, is going to be 2 amperes. So again, the primary current so the primary current, given that the voltage is a step-down voltage, we would actually expect that the primary current, given that you have a larger voltage, you'd have a smaller current. And of course, it's a step-down transformer, so your voltage gets smaller, your current gets bigger. Okay, and that's because power equals I times V must always be the same on either side of a transformer. All right, so let me do a couple of problems here. I mean, I did these, but let's do a couple more actual Openstack. These are examples. Okay, I'm going to do Openstack's 23.45. Okay, that says an American traveler in New Zealand carries a transformer to convert New Zealand's standard 240 volts to 120 volts. So she's an American, so she needs to have her devices are going to need 120 volts so that she can use some small appliances on her trip. All right. So A, what is the ratio of turns in the primary and secondary coils? So what is the ratio of turns? In her primary and secondary coils. Or sorry, in the primary and secondary coils of her transformer. B, what's the ratio of input to output current? C. How could a New Zealander traveling to the United States use the same transformer to power, use the same transformer to power her 240 volt appliances? From 120 volts. All right, so an American traveler in New Zealand carries a transformer to convert New Zealand's standard 240 volts to 120 volts so that she can use some of her small appliances on her trip. A, what is the ratio of turns in the primary and secondary coils of her transformer? B, what is the ratio of input to output current? See, how could a New Zealander traveling to the United States use the same transformer to power her 240 volt appliances from 120 volts? Okay, so let's remember all this, a lot of words. So the idea here is that, well, we'll start with the basic transformer equation. So B sub S over B sub P is N sub S over N sub P. Okay, that's the main transformer equation. Now let's what we want is, if we read this carefully, part A says, what's the ratio of currents in the primary to the secondary coils in a transformer? So the way this is written as a ratio of secondary to primary. So let's write it, let's flip the equation upside down. We really want the ratio of primary over secondary. So we can flip the equation upside down. All right. And so, well, what do we know? Well, make it equal to the number of N sub P over N sub S on the left-hand side, B sub P over B sub S. Well, essentially, when she goes to New Zealand, she's going to be plugging her device into a wall in New Zealand. All right. So in New Zealand, B primary out of the wall over there will be 240 volts. Okay. But she's used to her appliance requires 120 volts. So the secondary, so the primary will be out of New Zealand's wall, out of a wall in New Zealand at B primary 240 volts. So a transformer will step down the voltage to the level that she needs for her appliances. So her B secondary then would then have to be 120 volts because that's what her appliances need. All right, and so in that case, in my equation, I would just say, well, that's going to be 240 volts over 120 volts, and that's just equal to 2 to 1. All right, and so N sub P over N sub S is really a 2 to 1. The number of coils at the primary end of the transformer needs to be twice that at the secondary end in order to make this work. what about now? So now we have this. What about the current? Okay, so we'll kind of keep this in the parking lot. We know this now. We know that the ratio of primary to secondary coils, number of coils, has got to be 2. So we got that from part A. Now let's go to part B. Now we want to talk about the currents. All right. The current will basically say, well, okay, well, part B says, what's the ratio of the input to output current? All right. So what's the current equation? Well, again, a transformer equation is probably most appropriate for us now that we know this information. Is I sub P over I sub S. Remember, is N sub S over N sub P. It's flipped. So we want the ratio of the primary to the secondary. Okay. Well, that's going to equal what? Well, if N sub P over N sub S is 2, this is going to be 1/2. So I sub P over I sub S is going to be 1/2. The ratio of the currents will be half. The primary current will be half that of the secondary current. All right, what about part C? What if, on the other hand, I have a New Zealander, let's say she goes over to New Zealand, she makes a friend over there, and she hands her friend her transformer. Could her friend use it to go visit her in the United States? Well, yes. A New Zealander, so part C simply is this. A New Zealander can simply use the same transformer backwards in the United States. So all I have to do is use the exact same transformer from the New Zealander, and I can just hook it up backwards. That way I'm getting the opposite ratio that I need. Okay, let's look at Openstack's 23.47. Okay, that says A. What is the voltage output of a transformer? Used for rechargeable flashlight batteries. Used for rechargeable flashlight batteries. If its primary has 500 turns, its secondary 4 turns, and the input voltage is 120 volts, like again, coming out of the wall. right, and then B. B says, what input current is required to produce the 4.00 ampere output? So what input current is required to produce a 4.00 ampere output? And then finally, C, what is the power input? Okay, so here we go. So 23.47 open stacks. A, what is the voltage output of a transformer used for rechargeable flashlight batteries if its primary has 500 turns, okay, and that's your N sub P, as secondary 4 turns, that's your N sub S, and the input voltage is 120 volts, that's your V sub P. Input means primary. B, what input current, I sub P, don't know it, is required to produce a 4.00 ampere output, I sub S, 4.00 amperes. And then what is the power input? All right, so let's work it out. Again, we have to, again, as you're reading along, you have to translate what that means in your in the nomenclature of transformers. All right, so I do not know V sub S. Okay, I do not know the secondary voltage, but I know the number of turns in a primary is 500. The number of turns in the secondary is 4. And of course, the primary voltage coming out of the wall is 120 volts. All right. So again, what I want to use is the and again, what else do I know? I also don't know the primary current, which I'm going to look for in part B, and I do know the secondary current is supposed to be 4 amperes. All right, so let's just kind of write everything down, and I'll go one step at a time. Part A wants me to find the secondary voltage. Again, I go straight to the appropriate transformer equation, which would be V sub S over V sub P is N sub S over N sub P. I'm looking for V sub S, I just cross multiply the V sub P. The V sub S is simply V sub P N sub S over N sub P. All right, so that V sub S, what is the primary voltage? Well, that's what's coming out of my wall, 120 volts. N sub S, the N at the secondary is 4 turns. The N at the primary is 500 turns. So V sub S is going to equal 0.96 volts. So it's definitely a step down transformer in a big way. Stepping down from 120 volts out of the wall to just 0.96 volts at the secondary of the transformer. All right, so now we know this. So that's 0.96 volts. That's part A. Part B wants to find the primary current, the current out of the wall. So you see you have a larger voltage going to a smaller voltage. You should see a smaller current going to a larger current. So your answer should definitely be quite a bit less than 4 amperes. All right. And so let's see what it is. So let's look at the appropriate equation. So I think the appropriate equation for this would be I sub P over I sub S is N sub S over N sub P. Okay, again, what do I want? well, I want the primary current, so I'll just cross multiply. So I have I sub P is I sub S times N sub S over N sub P. I sub P is again the secondary current. I know that's 4 amperes. N sub S over N sub P. Well, again, N sub S is small, 4 over 500 is N sub P. So I sub P, as I predicted, is a small current, and that's going to be 3.20 times 10 to the negative 2 amperes, or we can write that as 32 milliamperes. And that's the current at the primary coming out of the wall. That's the draw out of the wall. All right, so I know that now. I have one more part of the question. I want to find the input power. So that's the power. That's the input power means the power at the primary, which would actually be the same as the primary power of the secondary. But again, particularly it does say input power, so we want to try to focus at the primary. So the input power would then be P sub P. Power at the primary is I sub P, V sub P. Product of the current and the voltage. And we know all this now. The power at the primary is the current at the primary. Well, that's this. We just got them calculating. So 3.20 times 10 to the negative 2 amperes. And the voltage at the primary, that's the voltage coming out of the wall, 120 volts. I do this, the power at the primary is going to be 3.84 watts. There you go, that's 23.47 C. All right, so the next topic that I want to cover briefly is safety. So again, I talked about safety a while back, and that's the thing about electrical electrical experiments is that yeah, you could get hurt in physics 1 as well. You can drop something heavy on your foot or something. You can get hurt there, or somebody's doing the uniform circular motion experiment and they hit you in the head with the ball or something and it's tied to a string. I mean, all these things can happen, right? But you have a much greater chance of really hurting yourself, possibly even killing yourself, in an electrical laboratory. So again, this is one of those things that, and again, when you're talking about electrical appliances, now instead of going to really electrical laboratory, now we're just really talking about electrical appliances. Like what is in your house? What are the safeties in your house? Safety features in your house. So again, when we talk about electricity, you need to have protection against hazards built into the electrical appliances that you use. All right. So again, let's talk again about electrical safety. All right, and so as I mentioned a couple lectures ago, there are two main hazards. In electrical systems. And we know them as a thermal hazard and a shock hazard. So again, the thermal hazard occurs when there's electrical overloading you might have a short circuit, you have too much current going through. A shock hazard your other kind of hazard occurs when electric current passes through a person. Again, we have two different hazards. And so we generally want to have our system that we have set up to have some sort of a safety features in it. So let me show you a picture out of Openstacks. Give me a moment here. I'll kind of talk through this picture a little bit. And let me get to the right spot in the book first. All right, let me share my screen. All right, so you might want to set up a basic system like you see. Now you see that little tiny sine function that you see. And so I'm looking at this upper picture right here. That little tiny wavy line. That is like a little part of a sine function. What that really means is that you have AC and AC voltage there. You see a little wavy line, that means that your voltage is AC. All right, it's alternating. And you have something plugged in, like again, any kind of appliance is plugged in is considered a resistance. All right. But again, that's a schematic that shows absolutely no safety features whatsoever. What you really want is you really want to look like the next picture. Now, the next picture, you see a number of different safety features. I'm just going to walk right through them. I mean, I want to kind of maybe make this more of a qualitative discussion here, but you see a schematic that this is how you really should have a power distribution with safety features. So most households have what's called a 3-wire system. So you notice that if you plug in, a lot of things, there is 3 prongs in there. Your output, your outlet has, 2 plugs or 2 parallel plugs, and on the bottom is like a third. So if you imagine for a moment, most households that are wired for safety, if you look at your plug in the wall, it's for a 3-wire system. So again, if your house is wired for safety, it should be wired. So most households are wired for a 3-wire system, as it's called. How do you tell? When you look at your wall outlets, let's say this is your wall outlet right here, you should see 2 parallel holes where you can have a plug, and then on the bottom you should see another hole. Again, this is wire 1, 2, and 3. You wired the 3rd wire for a neutral, usually for grounding with the earth. You want to try to ground your system as many ways possible so you get paths to the earth. Let me go back to sharing my screen. So now old houses and also old appliances will oftentimes just have a 2-wire system. So sometimes when you plug something in, you only have you really only have plug that has that really accesses the two top holes and leaves the bottom hole undone. What that just does is that just gives you a little less safety there, as you don't have the grounding. All right, so the three-wire system is a safety feature. You also have the fuse. So you notice here on the side here, so you have a picture of a fuse. That's your circuit breaker. So again, this black wire, the hot wire, is where your actual current's going through. So it's going to be connected in series with a circuit breaker. So if that circuit breaker experiences too much current, it's going to blow the fuse. So you certainly want your fuse wired schematically. You want your circuit breaker wired schematically with, or the fuse wired schematically with the hot wire. Okay, that's again another safety feature. Now, there's also a protective case that you see around whatever your appliance is. Could be your toaster. Oftentimes, there's a protective case around it. That protective case allows you to not be able to get in direct contact with the hot wire. Okay, the hot wire is you want to try to, in any way possible, is not have direct contact with that hot wire. You notice that case is grounded. All right, and so again, it's a protective case that helps you not get in direct contact. But the three-wire connection allows you to have grounding. So you try to ground the system as many ways possible. So you see grounding. There's three different grounds here. The symbol for grounding is this symbol right here that has it looks like a line with descending smaller lines. And I'm kind of moving my mouse around one of them right here. There's three of them, three right next to each other. All right, so you want to ground to 0 volts. So you want to make sure that you, as the person walking around the house, are walking around at 0 volts, and you want to make sure that your device in the wiring, and so you have the neutral wire, in the system, that should be grounded, and actually the case itself should be grounded. The case itself may develop a different potential, so you want to ground the case. If you don't ground the case, you can have a shock. All right, so there's a possibility of a shock in that case. So again, you want to try to maximize all the various earth ground connections. Now, when we try to, and again, I'm not really writing much on the board here, I'm kind of talking through this picture. You have different color schemes. So if you're a person wiring up, you're an electrician wiring up some appliances, you try to adhere to color schemes. But the color schemes may be regional, I should say. So you're really not sure. You have to always be sure what region you're in. So you have various color schemes of your wiring. All right, and so let me kind of go to my board here and kind of discuss a little bit on the coloring schemes. You try to color the wires with respect to some sort of coloring scheme, but they could very well be regionally dependent. So typically, your live, otherwise known as your hot wire, your live or your hot wire, they typically could be colored brown, red, black, blue or gray. Various colors that these wires have in various regions. They mean, the red wire, I'm not really sure what the wire coloring scheme is here in the United States, but depending on where you are, you need to know what you expect your live or hot wires to be colored. You're going to go and do anything with electronics. Your neutral wire, your neutral wire can take on also several different kind of colors. It's typically either blue, black, or white. And again, there's a little confusion, as you can see, because depending upon your region, you see some colors that are used twice. Depending upon your region, black or blue might be live or hot. Black or blue could also be neutral. So you got to be very, very sure, you know, by looking at the standards in your particular region, what are the colors for your wires. And then your ground wire is your third one, and that's usually oftentimes the easiest. Your ground wire, typically your ground wire is the one that's it's often it's most of the time green, you know, green earth, ground, but sometimes it could also be yellow or even bare. So again, you know, oftentimes your ground wire is a safe bet that it's green. But again, you have to look at the region. So again, there's a color coding scheme. This was actually developed, believe it or not, in World War I, because we needed to have soldiers in the war to actually be able to, you know, if your job was picked to being an electrician, some of these soldiers, and this is why, you know, the draft worked back then and it doesn't work today. Some of these soldiers were practically illiterate. They came off the farm and they didn't really have good schooling, and so they came in there and they were expected to try to understand things. So they had this whole color coding scheme to allow for people who had very low level of literacy to be able to still be functional. Now this coloring scheme has existed to this day. And so oftentimes, you know, back then you had a draft because you didn't necessarily have to be technologically advanced to be in the military. Today, a draft doesn't work. Why? Because the military is too technologically advanced. You really have to have, and then also there are people who want to get into the military. I mean, it's a good career. You want to get into the military, and so there's enough people who want to get in. You also don't need a draft. But again, the general rule is, I mean, you don't have, you know, the United States has a relatively high level of literacy, and you know, compared to the rest of the world. So, but this was not the case back in World War I. So the whole concept of color coding was to allow people who came from, you know, areas, maybe rural areas where there wasn't very good schooling, to be functional in the military as an electrician. All right, so you have to be very careful. Some cases, you know, some color codes are striped. You know, for basically for colorblind people. So I myself am somewhat colorblind. I actually failed the military colorblindness test. I mean, so again, I would appreciate something like this. Now I could see red, green, and blue. I could see red, yellow, and green stoplights, and I could see, you know, most saturated colors I can see. But when the colors are a fine difference, like in camouflage, I would have all kinds of problems. All right. So you also have, you know, oftentimes you know, when you're buying a house, you'll hear about GFI. And that's particularly in your bathroom and your kitchen. So GFI is stands for ground fault interrupter. Or GFI. You know, these are primarily in kitchens and bathrooms where there is a greater chance of water being on the floor. All right, so the ground fault interrupt So let me get a little. So again, we're talking about GFIs now. And so again, this is part of our last thing on electrical safety. The GFIs, how they work. So GFIs, they compare the currents in the live hot and neutral wires. So they compare those two currents. Essentially, when the live, hot, and neutral currents are not equal, it is almost always because the current in neutral is less than the live hot wires. All right, and so essentially, when that's the case, it's assumed that the path presents a hazard. Okay, and when that happens, now let me write this up here. So when this is the case, so when you have this difference, all right, so it's assumed that this path, that the path discussed below, presents a hazard. All right, so when you have this difference, and GFIs are usually set all right, they're usually set to interrupt the circuit if the leakage current is greater than 5 milliamperes. And that 5 milliamperes is that's the basic current that is harmless. That's the maximum harmless current. All right, so that's which, so if you get that shock, it's not going to be so bad, which is the maximum harmless currents. If shocked. So again, you know, it'll allow that maximum current to allow enough leakage current for that to equal that maximum current. Otherwise, now we have a hazard. Okay, so even if the leakage current goes to ground, so even if the leakage current goes safely to ground, through an intact earth ground wire, the GFI will still trip. Forcing repair of the leakage. All right, so again, that's just the GFI, again, another safety feature. And so the 3-wire system, you know, with the extra, you know, basically the with the and then of course the case, the safety case that goes around the appliance, and grounding the safety case, grounding the neutral wire. All of these are safety features, and on top of that, in cases where you have like the bathroom or kitchen areas, having GFIs, ground fault interrupters, are also yet another safety feature, you know, that tries to prevent shocks. And of course, the fuse, you know, prevents the thermal overload. So again, the hazards, the fuse prevents the overloading of the current of the circuit. That's a thermal hazard. And all of the grounding and the GFIs prevent further shocks as well. And you know, those prevent shock hazards. All right. And so again, this is you know, you always have to be thinking about safety when you're talking about using electrical appliances.